Hi everybody and welcome to this third video in the proteins videos series. So in this video we will discuss about isoelectric point of amino acids. Amino acids are amphiprotic compounds, meaning that they contain both a basic group NH2 and a acidic group COOH, and a general formula of any alpha amino acid is as follows. Right. So this alpha amino group is weakly basic. And this is acidic. So in a dry solid state, in a dry solid state, amino acids exist as dipolar ions. Now just write is dipolar ions, a form in which the carboxylic group is present as carboxylate ion, which is CO2 minus. This is your carboxylate ion, and the amino group is present as aminium ion, which is positively charged NH3 plus. Okay, so these dipolar ions are also called as Zwitter ions. Also called as Zwitter ions. The word Zwitter in German means hermaphrodite, meaning both this and that. So a molecule that contains equal number of positively charged and negatively charged functional groups is called as Zwitter ion. Yes, Zwitter ions. Okay. So if in a solid form, if they are present as Zwitter ions, in aqueous solution what happens is an equilibrium exists between the dipolar ion and the anionic and cationic forms of an amino acid. So So if this is some R group, neutral R group, so your this is the cationic form. So this is your dipolar ionic form. So this is cationic form. This is your anionic forms. This is your dipolar ion or deuterium. So there exists an equilibrium in these three ionic forms. The predominant form of an amino acid present in a solution depends on the pH of the solution and on the nature of the amino acid. For example, in a very strongly acidic solutions, all amino acids are present as cations. In a strongly basic solution, they are present as anions. And there is a point called as isoelectric point. Isoelectric point is the pH point called as Pi is the pH at which the concentration of the dipolar ion or deuterium is at its maximum. And the concentration of anions and cations are equal. Okay, so and each amino acid has a particular isoelectric point. Before we move into calculation of isoelectric point, it is important to bring a certain equation from your equilibrium chapter from 4th semester. So that equation is called Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, okay, which states that pK is equal to pH plus log of concentration of acid and concentration of base. Now a lot of students get confused here whether acid will be in the numerator or in the denominator. It can happen anyways. Now since you have written plus here, see, it is when you written plus it has to be acid. That is one nice way to remember. Here plus and acid, right? So that's how you remember it. Now when acid is Ha, acid, and base is it, and A minus is its conjugate base, right? So your pKa will become pH plus log of concentration of Ha divided by concentration of A minus. So this is your Anderson-Hasselbalch equation. Now when acid and concentration of acid and base are equal, so what happens? This term is becomes 1, log of 1 is 0, so your pKa becomes equal to pH. So this is all you need to know for calculation of isoelectric point. So let us study for alanine, a very simple molecule, amino acid. So calculation of isoelectric point. For a simple alanine, your structure happens to be CH3, NH2. This is your alanine, right? Okay. Now, when alanine is dissolved in strongly acidic solution, for example, at pH 0, if your pH is 0, okay, alanine is mostly present in its net cationic form. So, which is your CH3, C, NH3 plus. Okay, this is its net cationic form. In this state, amino group is protonated and the carboxylic group is neutral, which means it bears no formal charge. So all in all, the net positive charge is +1. Net charge is +1, therefore it is in its cationic form. Okay, and here the pKa of the carboxylic acid hydrogen pKa for the carboxylic acid hydrogen is 2.3. Okay, this particular proton is 2.3, and the protonated amino group of an when it's alpha amino acid is also acidic, but the pKa of this aminium group proton aminium group proton aminium group hydrogen is 9.7. So which means when base is added, base will attack this proton, base will take away this proton. So when base is added, an equilibrium is set up and the loss of proton is shown as below. Yeah, I'll just put Okay, so when base is added, this particular proton is removed first, and not the aminium ion proton, because its pKa value is greater. As simple as that. Okay, so the pKa of here is 2.3, the cationic form, and the pKa of the zwitter ion. Let me write it off. Cationic form. Zwitter ion form pKa 2 is 9.7. Now, when furthermore base is added, OH minus, what level? Then it will remove the aminium ion proton. So this is your neutrally charged. So it is NH2. So this is your anionic form because it has a net negative charge. And so what happens is, so why this happens? How the transition happens from, at a lower pH, and when you increase the base concentration, it will become anionic form. So this again depends on your Anderson-Hasselbalch equation. That is why it was introduced before. The isoelectric point of an amino acid is the average of these two pKa's. So pKa, your Pi is your average of pKa1 plus pKa2. So here let me calculate. That is half of 2.3 plus 9.7. So which is, I think, 6. Okay. So what happens when base is added to a solution of net cationic form? The first proton removed is carboxylic acid group, as has been already told. In the case when your pH reaches 2.3, okay, carboxylic acid proton will be removed from half of its molecule. That is because of the your Anderson-Hasselbalch equation. What is your pH? pKa will be equal to pH plus logarithm of concentration of acid divided by concentration of base, right? So because of this, when when pKa becomes 2.3, okay, this constant from half of the molecules, proton would have been taken away. Now when more base is added, alanine reaches its isoelectric point of 6.0, the pH at which all of the carboxylic acids protons have been removed, but not its aminium proton. So the molecules are therefore electrically neutral in their dipolar ion or zwitter ionic form, because the carboxylate group carries -1 and the aminium group carries +1. So the isoelectric point of alanine is 6.0. Now as we continue to add more bases, protons from the aminium group will begin to be removed until at pH 7, where protons from half the molecules of these zwitter ions will be removed. When further base is added, all the protons from aminium group will be removed, and you will get its anionic form. So your a graph of pH versus molar equivalence of base will look something like this. Yeah, tell me. Oh, done. Coming. So the graph of pH versus the molar equivalence of base. Base is, there is a, which is 6 as here. So it's something, okay. So this at half molar concentration, what happens is the pKa 1 is 2.3. At 2.3 pH, your cationic form NH3 plus is present. At your Pi, which is isoelectric point, at pH Pi is equal to 6, what happens? Your zwitterionic form is present. And then at your 2 molar equivalents, all the molecules are present in their anionic form. So this was the isoelectric point of alanine. Now if a molecule contains a side chain that has acidic or basic groups, the equilibrium becomes little more complex. So consider lysine for example. Okay. The amino acid, this particular amino acid has an additional NH2 group on its delta eta carbon. So in strongly acidic form, this is present as, okay, let me write the basic structure of lysine. Okay, alpha, no, this is your carbonyl carbon, alpha carbon, beta carbon, gamma carbon, delta carbon, and beta carbon. And beta carbon, there is an amine group. So this is your general formula of lysine. Now what happens is, at a lower pKa pH, there is a dicationic form of lysine is present, which means because there are two amine groups, the form that is present is dication. Okay, so this is your dication of lysine. Okay, the pKa of this carboxylic acid hydrogen, this is pKa 1 as 2.2, and it is OH minus and H3O plus. What happens is, your carboxylic hydrogen is removed. So this is your monocationic form of P. Here the pKa 2 of this particular proton, this proton is 9.0. Now when further base is added, this is your OH, when some more base is added, what will happen is, again, okay, so this is your monocationic form, this is your dicationic form. Okay, yeah, so this is your dicationic form. So what happens is, this proton is removed next. Next to, so this is your zwitterion form. and the pK of this particular proton, pK3, is here 10.5. Now when further base is added, what happens is this next proton is removed, okay, and this is your anionic form because there is a net charge of -1 here. So the isoelectric point of lysine is the average of this particular pKa and this particular pKe. So it is, so this is your 9.8 is the isoelectric point of lysine. Now similarly you can calculate of various, so I'll do one more, I'll calculate for glutamic acid and I'll calculate one for histidine. The glutamic acid is here, the formula is this is your formula of glutamic acid. Okay, there is a hydrogen. So it has three important pKs are three pKs are important. I'll just write it. So first is okay. Now here when you add base, the pKa 1 is 2.19, so which means this particular proton is removed when base is added. Okay. So then when next some more base is added, the proton that is removed is this particular proton. So the pKa of that particular proton is 4.21, 4.25, and what you get is your zwitter ion form minus this is a zwitter ion form, not later. This is your zwitter ion form. This compound, this molecule is zwitter ion. This is your anionic form. The pKa 3 of this particular anion is 9.67, Now this proton is removed, one of the protons is removed here. I'll just write it as okay. So this is your dianion form. Therefore, the isoelectric point is pK1 plus pK2 divided by 2. So that is your 2.19. See, you should, the corresponding pKs, that the zwitterionic form and the previous will be the average of those two pKs will be your isoelectric point. 4.25 divided by 2, that is 3.22. Okay. So now